Before we actually get around to solving systems of equations, I want to show you one of the most important tools that we can use to look at or analyze a system before we get around to solving it. This is the phase plane. It's a similar idea to a slope field. It's a little different though. We've actually seen a phase line very early on when we talked about slope fields. We talked about how if there was an autonomous equation, the slope field would be the same as you trace from right to left. In other words, for each value of t, um, the well, as you trace for different values of t, the slopes would stay the same as you look across. So you could just take one vertical slice and get all the information you need. And so we drew a phase line in those examples by just taking one thin slice of the slope field and pointing out where the equilibrium solutions are and then what direction everything is heading toward or away from the equilibrium solutions. So for an autonomous equation, the slope field can be sort of reduced down to a phase line, and that contains all the information you need. But really it highlights equilibrium solutions and it highlights directions that things are traveling. And those two things are important to keep in mind because as we move up to a phase plane, we're going to still look for the same thing. We're going to look for equilibrium solutions and we're going to look for the direction that things are traveling. But it's important to keep in mind the difference between a slope field and a phase plane. A slope field graphs the response of one equation to time. So you can look to the right to see the long-term results or the long-term solution. The phase plane instead doesn't have an axis for time, but now if we have two solutions, x1 and x2, we can graph one versus the other. Now we're going to call them x and y throughout this section just to make it simpler. Graphing is more familiar with x and y than with x1 and x2, but it's the same idea. We have two solutions we're looking for instead of just one. Now if we had a system of three equations, we would have to draw a three-dimensional picture. We're not going to go to any of those just because they're harder to visualize, and all the ideas that we need we can get with two-dimensional ones. But in theory, you can draw three-dimensional phase pictures, phase portraits, they call them. So time isn't on the picture, but we do include, when we draw arrows, we put direction to them to indicate which direction they're traveling over time. So if all we drew was a little segment like this, it wouldn't be clear whether it's traveling this way or this way. So we'll put a little arrow on it to indicate the direction of time. So it's kind of similar to implicit graphing implicit solutions or equations where you include time as this sort of third piece to the picture. So these are for autonomous systems. That's where we can do this because then we don't have to look at the solutions over time. Since they're autonomous, they don't depend on time. If they do, then we can't draw these quite as easily. So here's a simple example of a short system, two equations. Notice again they're coupled and they're autonomous. There's no values of t here. So at each point, just like we did with the slope field, you're going to pick a point on the grid, and then for each one you draw a little line segment that points along x prime, y prime. So the vector x prime, y prime describes at this point where is it going to go. So for instance, at 1, 1, x prime equals negative x, and y prime equals negative 2 times y. So what that means is if you're at the point 1, 1 right here, then if you take one step forward, x is going to go down by 1 and y is going to go down by 2. So that would look like something heading in this direction. Maybe more like this. So it's basically moving to the left 1 and down 2. So x prime and y prime, again, are just the change in essentially one step forward in time in this process. And you can continue doing this. You could do it for 2, 1, and then 2, 2, and 1, 2, and so on. Right? So you can draw these arrows, and it, again, just like slope fields, it very quickly gets tedious, and we don't want to do this by hand if we can avoid it. So instead, we'll let a computer do it for us. Because what's more interesting for us is being able to interpret them and read a phase plane to gather the useful information about a system of equations. So to do this, I'm using an app on the iPad. It's called Slopes Differential Equations. So if you have an iPad or iPhone, you can look at that app. There are other things you can use to do this. Desmos can draw phase planes for you, and I'm sure you can find other tools that'll do it. You can do it in MATLAB and so on. But this is convenient just because it very quickly lets us draw lots of different slope fields. So I don't know if you can read these values here. Let me write them down more clearly. What we have is we have x prime equals negative x, and y prime equals, what do I have, negative 2y. So that's the example that we just did by hand with a couple of points, but this is the full thing with many more points graphed. Now what you notice is these arrows are all pointing in toward the origin. So what we can do, just like we did with slope fields, is we can draw a few representative solutions. So let me draw a couple of these. So if I start somewhere out here, I would follow these lines in toward the origin. If I started somewhere here, I would do the same thing. And then if I started down here, same thing. Following the arrows leads us into the origin. And so all roads lead toward the origin. So you've got everything, every solution trends down toward that. And what that means is that this point, the origin, is essentially the long-term solution. It's where things are heading toward, which hopefully reminds you of equilibrium solutions when we did slope fields. And it's the same idea. So that's, again, an equilibrium solution, an equilibrium point. It's also called a critical point. So either term means the same thing here. You've got a equilibrium point or a critical point. Because the solutions are all trending toward it, and it's therefore a stable equilibrium. Again, remember we talked about that a lot with slope fields back early on in the semester. Things are trending toward it. It's a stable equilibrium, and it's also called a sink. And the idea of sink is that things sort of drain down toward it. It collects things toward it. So solutions tend toward it. If it were unstable, it would be called a source, which kind of pushes things out from it. And again, the idea it's a stable equilibrium, that's the other way of saying that it's a sink. Specifically, it's asymptotically stable, meaning in the long term, things are trending toward it. It's a stable equilibrium. So that's a picture of a stable one where things are all trending down toward one point. So as far as phase planes go, you should have a sense of how they're drawn. For simple ones like this, I might ask you to draw a simple one with just a few points. But more importantly, it's necessary that we understand how to read one and how to interpret it. So let's look at a few more examples, and I want to show you some examples of different kinds of pictures that you can have sources and sinks of different types. And it basically all depends on what your system of equations looks like and what coefficients you have in different places. So let's look at a few examples. Here's one where we have a system x prime equals 5x minus 3y minus 2, and y prime equals 4x minus 3y minus 1. So I've drawn this using the same app, and on this app also I've gone ahead and plotted a few representative solutions so that I don't have to draw them by hand. And you'll notice as you look at the arrows and you look at these solutions, you can kind of see this behavior is a little bit quirky. It's a little bit different than the last one. As solutions come in, they tend to do something like this and then like this. And so what's happening is that there's a line right here, and there's a line right here that are kind of like two asymptotes. That's not drawn very well. hard to draw these correctly. But anyway, knowing where that center point is what's interesting, and we'll think about that in a second. But if you notice, as things trend in along this first line here, along that line, things are trending inward toward the origin, right? So notice that things are pointing in like this, along this line. And then as you move away from that line, around it, stuff kind of curves away. But otherwise, along that line, things are moving in. And along the other line, the trend is that it's moving outward. So there's these two lines that are really controlling the behavior of this. And we'll talk more about these when we have a little more background to talk about what solutions look like. But for now, if you notice this behavior, you're seeing two competing principles. One, the solutions are trying to trend toward, the other, the solutions are trying to trend away, which is what leads to behavior like this, where it kind of, if it follows this one, it's coming in, and as it gets closer, it starts following this one and heads outward. And so you get this unstable behavior. So if you're looking for where this point is, the dot right there, the equilibrium is where both of them equal 0. That's what it's trending toward. So the equilibrium is where they're both 0 because that's where things are not changing. And if you solve this system, basically you set these both equal to 0. And so you get 5x minus 3y equals 2, and 4x minus 3y equals 1. And I won't take the time to solve it, but if you do, you should get x and y both equal to 1. So it's hard to see on the picture, but that's actually the point 1, 1. It's not super clear from the way it's drawn, but that's the point at the equilibrium. Now the question is this a stable or unstable equilibrium? If you just look at this first line, you would say, well, it's stable because things are heading in toward it. It's a sink. Things are trending down toward the equilibrium. But if you look at the other one, you say, well, no, it's a source because it's trending away from it. So if you're right at the equilibrium, you'll stay there. If you're off the equilibrium a little bit on this one, you'll trend toward it. But if you're off the equilibrium a little bit on this one, you'll trend away from it. So it really depends on where you are as to whether you will trend toward the equilibrium or away from it, as to whether it's stable or unstable. So this is a special thing called a saddle point, because you have one solution or one part of it that trends toward the equilibrium and other parts that go away from it. The reason it's called a saddle point is you can draw a picture like this. It kind of looks like a saddle, if you can forgive my illustration skills. And on a saddle, if you were at this point up here, for instance, you might trend toward the center here. Or if you were up here, you might trend toward the center here, if you like put a marble there and let it roll. But if it's off that line at all, if you put it over here, it's going to roll off like this. Or if you put it over here, it's going to roll off like this. So if you put it right on that center line, it'll roll toward the center. But if it's off even a little bit, it will roll off and it'll be unstable. So it's a hybrid between stable and unstable, between being a sink and being a source. It's a saddle point. So it's kind of semi-stable in that sense, but we have a special name, the saddle point, for it. So if you see something like this case where they're all trending towards some point, that's a sink. If you see something like this where you have this some solutions trending toward and some trending away, you've got a saddle point where there's a combination of stable and unstable. So a few more examples I want to show you. Here's the predator-prey model. I don't know if you can see that, but if you can't read those constants, this is x prime equals 2x minus 1.2 xy, and y prime equals negative y plus 0.9 xy. And if you compare back to that Lotka-Volterra model, you'll see that I've just filled in values for A, B, C, and D. And these values are not significant in this problem. But what you can notice is the behavior of this, where there's this interesting cycling behavior. It sort of circles around and circles around. By the way, note that here we have the solutions of x and y. We have x of t and y of t. So this draws graphs for us for the solutions as well. And so again, I mentioned earlier that there's that cycling behavior, and notice that's what you see here. There's a cycling where as the prey increases, then the predators increase, and then as the the predator population gets too high, the prey population starts to decrease, and then the predator population decreases. So there's this cycling, and there's kind of this delay effect where after the prey population starts to drop, it takes a little while for the predator population to respond to that, and so then it starts to drop, and then as it drops, the prey population starts to go up again, and so on. So there's that cycling effect, and that's what you're seeing here. That solutions are cycling. They're just going around and around and around, and for a given initial condition of x and y, it'll just cycle forever, and there's this sort of stable pattern where even though there's oscillation, even though it's never trending toward a single point, it's still stable in the sense that it is going to continue on in the same pattern. It's going to continue going. So it's not going to fall apart. The populations won't collapse. There are cases where if you change the values too much, this population will collapse. But this is a stable one. So this is revolving around a center. So this is still a stable equilibrium. And the equilibrium point is right here. Right in the middle. So of course there's a trivial equilibrium there where if you start there, if you start at that point, nothing will happen. It'll just sort of stay there constantly. Those values will stay the same. So there's some value of x and y that is perfectly balanced where the birth rates and death rates would balance each other out and the populations would stay constant. But otherwise, if you start anywhere nearby, it's going to have this cycling effect to it. So you'll see something like this where it's kind of circling the drain and never going down toward it, but it still is a stable equilibrium, stable circular patterns like this. Here's another example, and again, it's a little small, but you can see this. It's the same idea. You still have a stable center. These, the circles or the loops are like elliptical like this, but it's the same idea. You still have this cycling around, and for different initial conditions, you have a different one of these curves that starts building a pattern like this. So that's an example of a stable one as well. So you can have stable equilibria that look like this, where you have things trending toward a single point, or you can have stable ones that are cycling around an equilibrium and just going around and around and around. For a couple more examples of, here's another example of a stable one. If you look here, again, you'll notice that there's a few curves drawn here for you just to help visualize. But again, notice that based on the direction of these arrows, these solutions are again trending inward, all of them. So all of these are trending inward based on the direction of these arrows here. And so what you can look at here, it's not quite as clear as the previous one, but again, there's a line here where they're all clustered around. It's the kind of like an asymptote kind of idea. And there's another one which may be harder to see right here, which isn't quite flat, but it's close to being flat. Put it like that. And for this one, if you look along these lines, all of these have arrows pointing inward. So it's like that example we did with the saddle point, except in this case, they're all trending toward the equilibrium. So that's, again, a sink, which is stable, asymptotically stable. And no matter what initial values you have, no matter what initial conditions you have, everything is trending toward the equilibrium. And you could figure out where the equilibrium is by, again, solving that system of equations, saying x prime and y prime are both equal to 0. You could solve it and find where it is. But that's not quite as interesting at the moment, so we won't bother doing that. So you've got this, again, this sink, just like the first example, where everything's trending together. Even though the shapes look different, it's the same idea that you have a stable sink like this. This one is kind of the same picture, except all the arrows are pointing outward. So this would be a source, which is unstable. So this would be like when we talked about stable and unstable with slope fields. This would be like the pendulum that's pinned at the bottom, where if you let it go, it will leave its equilibrium, or like a bowl that's facing downward that you put a marble on top and let it roll away. So again, here we have some lines that kind of control this behavior, that form most of the behavior of it. They look like this, and then there's one kind of right here. And for all of these, solutions are all trending away from the equilibrium. So that's completely unstable, an unstable source. So we've seen sources, we've seen sinks, and then there's two more examples. Both of these are spirals. You'll notice that one of them, the spirals are all trending in toward the equilibrium, and the other one, the spirals are all trending outward. So the first one, where they're trending in, that's what we call a spiral sink. And that one, of course, is stable, asymptotically stable. And then we have a spiral source, and that one has that one's asymptotically or just unstable. So we've seen a bunch of examples. The textbook has them kind of laid out next to each other of different examples you can run into with phase planes. And over the next couple of lectures, we're going to be looking at how to solve systems of equations like this. And as we do, we'll use the phase planes and kind of see how the behavior of the solutions matches with these pictures. So you can kind of look through again and look at these examples as a set of, again, examples that you can compare different systems to as we go through and study them in more detail.